Question number 1. Value of resistance is given. There is only one component in the circuit, that is resistance of 100 ohm. Supply voltage is 220 volt. 220 volt should be taken as VRMS and frequency 50 Hertz. Then what is the RMS value of current in the circuit? RMS value of current can be calculated as IRMS is equal to VRMS divided by only resistor is there, so VRMS divided by R, you get the value of IRMS. Then what is the net power consumed over a full cycle? So we can calculate the power. The resistance is there, therefore we can calculate the power. P is equal to, either you can use the formula VRMS IRMS, or you can calculate, or you can use the formula IRMS square into R, so that the power consumed is obtained. Now next, question 2. The peak voltage of an AC supply is 300 volt. So V0 or VM is equal to 300 volt. What is the RMS voltage? So VRMS is equal to VM divided by root 2. VM is given in the question, so that VRMS can be calculated. Then the RMS value of current in the circuit is 10 ampere. What is the peak current? Peak current IM is equal to root 2 into IRMS. RMS current is given there, so root 2 into IRMS, so that you get the value of peak current. Next, question 3. A 44 millihenry inductor. VRMS is equal to 220 volts. Frequency is 50 Hertz. And if you have frequency, angular frequency omega, you can calculate using the formula 2 pi nu. Now, determine RMS value of current in the circuit. Here, inductor is the only component connected there. So, IRMS is equal to VRMS divided by XL is equal to VRMS divided by XL is omega L and omega is 2 pi nu, so 2 pi nu L. Substitute the quantities so that you get the answer. Now, question 4. A 60 microfarad capacitor, supply voltage VRMS is given 110 volt. Frequency is also given. Again, here also we can calculate angular frequency using the formula omega is equal to 2 pi nu. And you are asked to calculate the value of RMS current. Just like in the previous problem, we have IRMS is equal to VRMS divided by XC is equal to VRMS divided by 1 by 2 pi nu C. So substitute the values, you get the value of IRMS in the circuit. Now question 5. In question 3 and 4, what is the net power absorbed by each circuit or a complete cycle? Explain your answer. So here, in both the cases, net power will be 0, because power formula P is equal to VRMS IRMS cos phi, and the value of phi is equal to pi by 2. Therefore, cos phi is 0, so power is equal to 0. Now, question 6. Obtain the resonant frequency omega r of a series LCR circuit with the LCR values are given. Also calculate the Q value of this circuit. Okay, resonant frequency formula omega r is equal to 1 divided by root LC. Values of L and C are given, so that omega r you can calculate. Then Q value of the circuit. There are 2-3 formula you have studied for Q value. Any one of them can be used. 1 by root 1 by Q is equal to 1 by R into under root L by C, and quality factor can be calculated. Then question 7, a charged capacitor, capacitance is given 30 into 10 power 6 farad, inductor 27 millihenry. Then what is the angular frequency of free oscillations of the circuit, which means natural frequency you have to calculate. Again the formula, natural frequency of the circuit, omega naught is equal to 1 by root LC. In the question it is okay, natural angular frequency only you need to calculate. So substitute the values, you will get the value of natural frequency. Then question 8, initial charge in a circuit, that is from question 7, is 6 millicoulomb. Millicoulomb you have to convert. Then what is the total energy stored in the circuit? The values of L and C are given. The total energy is equal to, total initial energy is equal to QM square divided by 2C will give you the total energy of the circuit. Now what is the total energy at a later time? The total energy will be same in the case of an ideal LC circuit. Next, question 9. LCR circuit values of R, L and C are given. VRMS is given 200 volt. Again, what is the frequency of the supply equals the natural frequency of the circuit. So again, when you want to calculate the what is the when the frequency of the supply, okay, sorry, when the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred in one complete cycle? We know that when the frequency of the supply equals natural frequency, which means it is the resonance condition. Resonance condition power formula P is equal to VRMS IRMS cos. VRMS IRMS cos phi. Let resonance cos phi is equal to 1. So you get a VRMS IRMS. So that we can write as VRMS into IRMS can be written as VRMS divided by Z, and is at resonance Z is equal to R. So in this case, the total impedance of the circuit Z is equal to R. Therefore, you can use the formula VRMS square divided by R. VRMS is given in the question 200 volt, so that the power in one complete cycle can be calculated. Now, next question 10. In question 10, two frequencies are given. mu1 800 kilohertz and mu2 1200 kilohertz. Okay, if its LC circuit has an effective inductance 200 microhenry, what must be the range of variable capacitor? We know in tuning circuit. Okay, LC circuit is used in tuning circuit, and in tuning circuit we have an inductor, then a variable capacitor. So what is the range of capacitance? That is the question. So the capacitance we can calculate in such a way that we have mu1 is equal to 1 divided by 2 pi under root LC. That is the formula. Now square this formula and find the value of C1. C1 is equal to, you will get 1 divided by 4 pi square mu1 square L. Now substitute the values so that you will get a capacitance C1. Now replace nu1 by nu2, then you will get the value of C2. So that the range of capacitance is from C1 to C2. Now next question 11. It's an LCR circuit. Again RMS voltage, values of L, C and R are given there. Now next part A, determine the source frequency which drives the circuit in resonance. So source frequency, again we can use the formula omega naught is equal to 1 by root LC. Substituting the values, you can find omega. The question is it's not very clear. It's resonant frequency or frequency. Therefore, definitely you need to calculate frequency also. So frequency nu naught is equal to omega naught divided by 2 pi. So you will get the value of nu naught. Then next part B, obtain the impedance of the circuit and amplitude of current at the resonant frequency. At resonant frequency, we know Z is equal to, this part A and part B. At resonance, Z is equal to R. So you can directly write the answer will be 40 ohm, will be the impedance. Then at amplitude of current at the resonant frequency. Amplitude of current means Im you have to calculate, peak value of current, and peak value of current means peak value of voltage also we have to take Vm divided by Z, and Z is equal to R. And Vm is not given, only Vrms is given. So you have to take root 2 Vrms, means root 2 into 230 divided by R will give the peak value of current. Then come to part C. Determine the RMS potential drops across the three elements of the circuit. RMS voltage drop. So first of all, what you have to do, you have to calculate IRMS. Already we have Im is there. So IRMS you will get Im divided by root. You can find the value of IRMS. Once you get the value of IRMS, then you can calculate what is the voltage drop across inductor. So you will get VL is equal to IRMS into XL. IRMS into XL, while XL is equal to omega L. Omega is calculated in part A. So you will get IRMS into omega L. The value you can find. The same method you can calculate to find VC also. VC is equal to IRMS into 1 by omega C will give you VC. Then again you can see you have to find the same for resistance also. You have VR is equal to IRMS into R. So you get the value of RMS voltage drop here. Okay, so you can calculate the answers in this way. But here I want to mention certain points. First of all, you can see when you calculate VL and VC, okay, circuit is at resonance. Circuit at resonance means you know VL equal to VC. Therefore, in the second part, you need not go for a calculation. You just write the formula and directly write the answer what you have got in the case of VL, because VL is equal to VC. Now the value of VL and VC, when you calculate, you will get around VL equal to VC is equal to approximately 1437 volt fuel rod. And when you observe the value of VR, you will get VR is approximately 230 volt. Now here in this circuit, you have to see the conditions very carefully. Whatever voltage applied, that is 230 volt, that is dropped across the resistor. So then what about the inductor and capacitor? We know that the resonant condition VL and VC will cancel each other. So that whatever voltage applied is dropped across resistor. That is why VR you get 230 volt. That's the first point to be noted. The next VL equal to VC is equal to 1437 volt. So how will it happen? The applied voltage is only 230 volts, and according to our concept, Kirchhoff's loop rule, this 230 volt will be distributed among various components in the circuit. Then each component should have a voltage less than 230 volt because the applied 230 volt must be distributed. Then how do you get this 1437 volt? Okay, so here the first part you have to see, this is not the violation of Kirchhoff's loop rule, because when you take the total voltage drop in the circuit, VL equal to minus VC, so they mutually cancel each other. So Kirchhoff's law is valid here. Then second point, here you have to see what is the reason you get a voltage like this in the case of inductor and capacitor. You know, during the operation of the circuit, capacitor will be charged. So at the charging condition only you observe this very high voltage in the capacitor. So what is the reason the capacitor is showing very high voltage? It is due to the charging of the capacitor. Then what about the inductor? In inductor you can see, according to the variation of AC, back EMF is produced in the inductor. Back EMF is induced in the inductor. Because of the induction of this back EMF, only inductor is also showing this very high voltage. It is actually the back EMF, not the part of applied EMF. So back EMF, inductor shows high voltage due to the production of back EMF. Capacitor gives high voltage due to its charging. Okay, and still everything is in accordance with the Kirchhoff's loop rule. So the question you have to note very clearly, understand properly. Now come to question 12. LC circuit. Values of L and C are given. Initial charge Q is also given, 10 millicoulomb, 10 into 10 power minus 3 coulomb. Now come to the solution of part A. What is the total energy stored initially? Is it conserved during LC oscillations? Again, total energy formula, we have E maximum is equal to Qm square divided by 2C. We can substitute the values and find the answer. Then, is it conserved during LC oscillation? Again, the same answer. In the ideal LC oscillation, energy is conserved. Now come to part 2B. What is the natural frequency of the circuit? Natural frequency omega naught is equal to 1 divided by square root of LC. Substitute the values and you can find the value of omega naught. Once you get the value of omega naught, you can find the value of nu naught also. Natural frequency of the circuit. Now next, part C. At what time is the energy stored? Completely electric. Second part is also there, completely magnetic. So now part C, case 1. Energy is completely electrical. Energy is completely electrical means. We'll start with this formula of charge. Q is equal to Qm cos omega is equal to Qm cos omega can be written as 2 pi by 2 pi by t into t. Now, completely electrical means all energy is stored in the capacitor. When all energy is stored in the capacitor, we can have Q is equal to Qm is equal to Qm cos Qm cos 2 pi by t into 2 pi by t into t. Now Qm will be cancelled so that you will get a cos 2 pi t by t equal to 1. Which means what should be the value of small t, so that value of cos you will get to 1. So you can see that you will get this condition when t is equal to 0, cos 0 is 1. Then again you can see you can take t is equal to capital T by 2. When t is equal to capital T by 2, you will get cos pi. Cos pi is cos 180, that is minus 1. Minus 1 indicates that the capacitor is completely charged with the opposite polarity. That's all. Anyway, the charge is complete, so the capacitor is completely charged. The next we can see T. Then you will get a cos 2 pi. Cos 2 pi is again 1. So these are the values of T for which the capacitor is completely charged, so that the energy is completely electric. Now, next, take part 2. Part 2, that is completely magnetic. Completely magnetic means the capacitor is completely discharged. Therefore, Q is equal to 0. Q is equal to 0, that means 0 is equal to Qm cos Qm cos 2 pi by t into t. And for which, this value should be, what should be the value of t here, so that cos 2 pi by t into t equal to 0. So values we can just see. First we can take t is equal to t by 4. T is equal to t by 4 means cos pi by 2. Cos pi by 2 is cos 90 0. Then next you can take t is equal to 3t by 4. That means 270 you will get. So for these values, t by 4, 3t by 4, 5t by 4, etc., there is no charge in the capacitor. As there is no charge in the capacitor means the whole energy is stored in the inductor. So these are the answers for the first and second part of C. Now next, at what time is the total energy shared equally between inductor and capacitor? The total energy shared equally between inductor and capacitor. Okay, just assume that when total energy is equally stored, when inductor and capacitor are having equal energy, energy in the electric field is equal to energy in the magnetic field. At that condition, take charge in the capacitor is Q. Assume that charge in the capacitor is Q when energy is equally shared between inductor and capacitor. Then energy in capacitor, we can calculate. Energy in capacitor is equal to, okay, energy in capacitor is equal to Q square divided by 2C. So remember our assumption, when the energy is equally shared between inductor and capacitor, we assume that charge Q is present in capacitor, then energy in the capacitor is equal to Q square by 2C, and this energy is the half of the total energy, and total energy we know it is Qm square divided by 2C is the total energy. So when energy is equally shared, the energy carried by the capacitor is the half of the total energy. Now, you can simplify the equation. When you simplify the equation, you will get Q is equal to Qm divided by root 2. Q is equal to Qm divided by root 2. Therefore, you will get Qm divided by root 2 is equal to Qm into cos Qm into cos 2 pi by t 2 pi by t into t. Now here you can see Qm will be cancelled, so that you will get cos 2 pi by t into t is equal to 1 by root. Now you can find out for what values of t. 1 by root 2, you can see the angle should be 45 degree. So for what values of t, we get the cosine value 1 by root 2. That is what you have to calculate there. So here you can take t is equal to t by 8. When you take t is equal to t by 8, then t and t will be cancelled. So you will get a pi by 4. Cos pi by 4 is 1 by 2, 1 by root 2. Then again, if you continue, you will get the same answer in 3t by 8, then 5t by 8, etc. Okay, so that is the answer for part D. Now come to part E. If the resistor is inserted in the circuit, how much energy is eventually dissipated as heat? You know, if you connect the resistors, then heating effect will be there. Inductor and capacitor do not dissipate energy in ideal situation, while resistor will dissipate energy in the form of heat. So during the LC oscillation, whatever energy is possessed by the LC circuit will be lost in the resistor in the form of energy. So what happens, whatever value of energy you got in part A, I think you will get a 1 joule, something like that, that the whole energy will be lost in the form of heat gradually from the circuit. So whatever be the answer for part A, the same will be the answer for part E also. Now next, come to question 13. 13, you have inductor, resistor, which means circuit is an LR circuit. LR circuit. Then first question, what is the maximum current in the circuit? Maximum current we have to calculate. So here we have Im. Im is equal to Vm divided by Z is equal to 240 volt is VRMS. So we have root 2 VRMS divided by Z under root R square plus omega L the whole square. Again, frequency 50 Hertz only given, so omega is equal to 2 pi nu, and substitute the values, you get the answer for peak value of current. Then the second part, carefully you have to see what is the time lag between voltage maximum and current maximum. You know, there is a phase difference, tan phi is equal to omega L by R. That much phase difference is there between current and voltage, and you are asked to calculate what is the time lag between peak value of current and peak value of voltage. So here we can take V is equal to Vm cos omega. V is equal to Vm cos omega t, and I is equal to Im cos omega t plus phi. I is equal to Im cos omega t plus cos omega t minus phi, because in inductor LC circuit we can see current lags behind the voltage, cos omega t minus phi. Then we take at t equal to 0. At t equal to 0, we can see V is equal to Vm, which means at t equal to 0, voltage is the peak voltage in the case of in the circuit. At t equal to 0, V equal to Vm, maximum value of voltage. But here in the current, you see at t equal to 0, I is equal to Im cos phi will come. That means current is not maximum when t equal to 0. So for what value of time, current will be maximum? We can take t is equal to uh, t is equal to 5 by omega. When t is equal to 5 by omega, it becomes cos omega into 5 by omega. Omega will be cancelled. 5 minus 5 becomes 0. Cos 0 is 1. At that time, you will get I is equal to Im. Current becomes maximum, which means voltage is maximum at t equal to 0. Current is maximum at t is equal to 5 by omega. So what is the time lag, time difference between them? That time difference is you have to take the difference between the time at which you get the voltage peak and time at which you get the current peak. So you can see the difference between these two values is 5 by omega. Therefore, the equation for time lag is equal to 5 by omega. 5 by omega will give the time lag. Now, the next step you have to find out the value of phi and omega. Frequency nu is given, so omega you can calculate. Omega is equal to 2 pi nu. You get the value of frequency. Now, phi you have to calculate. How can you calculate phi? Here, tan phi is equal to omega L by R. Substitute the values of omega, L and R. You will get the value of tan phi. From tan phi, you can find the value of phi. And when you calculate the value of phi, the unit of phi should be in radian. If you are good in degree, then convert degree into radian. Then substitute in this formula pi by omega so that you can find the value of time lag between maximum voltage and maximum current. Okay, now next question 14. Answers to A and B in exercise 30. Okay, if the current is connected to a high frequency, the difference we have to see in this question, we have here 50 hertz current, while here 50 hertz frequency, while here 10 kilohertz frequency. So when you substitute that 10 kilohertz at very high frequency, you have to show that the inductor in the circuit nearly amounts to an open circuit. So what is the meaning of that? So you have to follow the same calculations here also, but we know XL is equal to omega L is equal to 2 pi nu L. When the frequency is very high, XL will be very high. That means circuit gives very high impedance. Very high impedance in such a way that the current even practically can't flow in the circuit. That is why, because of that high impedance, we can say the circuit behaves as an open circuit. Practically, it cannot conduct because of high impedance in the circuit. Where you are asked to prove, you have to find here also the value of Im. Follow the same method, only the difference is that the value of frequency will be different. Then here also you need to calculate time lag using the formula phi by omega, and Z value you will get a very high, which indicates that the circuit is almost non-conducting or it is an open circuit. Okay, now question 15, again the same, only the difference is that it is CR circuit. So whatever omega L you have substitute there, here also you have to substitute 1 by omega c. That's the only difference between question 13 and question 15. And there also Im you have to calculate. Im is equal to Vm divided by Z is equal to root 2 Vrms divided by under root R square plus 1 by omega c the whole square. Then time lag you can calculate t is equal to 5 by omega. Find the value of phi and omega, you will get the value of time lag also. And here tan phi value is also different. You know that tan phi value is equal to 1 by omega c r is the value of tan phi. Tan phi is equal to 1 by omega c r. Then again here also phi you have to calculate in radian and substitute there. Then question 16 is again same as question 14. Here also instead of 50 kilohertz, 50 hertz, you have to use a source frequency 12 kilohertz. High frequency has to be used. And in such a situation, again you have to calculate the value of Im using the same formula in question 15. Find the value of Im. Then again find the value of time lag t also using the equation t is equal to 5 by omega. And here again you need to find the value of z using the same equation. Z is equal to under root r square plus 1 by omega c the whole square. But in this problem you can see xc is equal to 1 by omega c is equal to 1 by 2 pi nu c. Value of nu is very high. When value of nu is very high, value of xc will be very small. Already I have seen capacitor is an easy path for AC. So as value of xc is very small, it's very easy for AC to pass through the capacitor. While you can see in the case of DC, already you have seen when we have discussed the theory, the capacitor having infinite offense against DC, so that what happens, the capacitor will block DC. So while due to the increase in frequency, you can see its reactance decreases. So in the case of AC, it can very easily pass through the capacitor. That is the result you will obtain from the value of Z.